Previously, I've talked about controversies in the cladistic classification of dogs, cats, bats, monkeys, turtles, ichthyosaurs, and of course humans. But there are more controversies in the classification of pterosaurs than in any other group I know of, apart from birds, and the controversies in avian classification are intertwined with pterosaurs too. So I'll be talking about both. To begin with, most people think of pterosaurs as flying dinosaurs. When I was a boy, I remember the other kids called them dinosaur birds, but they were neither dinosaurs nor birds. The first problem is that most people don't know any more about the fossil record than what they've seen in a few plastic pieces in a prehistoric playset. Not only do they typically think that all these things are dinosaurs, they might even think that these are all the fossil forms that are known. They have no idea how rich the fossil record is. Just to make this easy for you, I'm going to remove all the actual dinosaurs from this image, all except one. In the top right-hand corner, there is a yellow terror bird. Now, that actually is a dinosaur, just like all birds are, and I'll explain that momentarily. But the two pliosaurs beneath it are not dinosaurs. The three specimens closest to the tree at the bottom are mammal-like reptiles from a time before the dinosaurs. A lot of people aren't even aware that there was a time before the dinosaurs. At top center, there is a pair of pterosaurs, and everything else here is a mammal. Now, some creationists, like Carl Gallups, think that even mammals are dinosaurs, but that just shows that he doesn't know what a dinosaur is. Not everything that is big and dead is a dinosaur. A lot of people think that dinosaurs are giant lizards, which is slightly closer to the truth, but that's not right either. Now, before this gets too confusing, let's put some structure behind this. We'll look at the tree of life. There are many ways to represent this, but I find that this familiar format is the best way to illustrate the concept of monophyletic clades. Notice that each of these folders is a clade, which encompasses all of its descendants and which is marked by the emergence of diagnostic traits, known as synapomorphies. We'll use this cladogram as a sort of evolutionary roadmap so that you won't get lost as the talk continues. We're just going to skim over this, jumping down to animals, then bilaterally symmetrical animals, and from that group we'll select animals with backbones, then those with jaws, and from that group we'll go through the ones that have legs and that also have feet and toes, and we'll select amniotes. This is the group we want to start with, tetrapoidal vertebrates which develop in amniotic fluid. This is one of the most important steps in the transition to living on land. From this point they continue to branch out. This first subgroup are synapsids. That includes mammals and a whole bunch of extinct transitional forms that are mammal-like or very nearly mammals. The next clade begins our reptilian collection, but this first set are not quite reptiles, they're para-reptiles. This is where you find turtles and turtle-like things. There are some controversies here too, but I've already done a video about those. In the folder of newer forms, we have diapsids. These are the true reptiles. So excluding all their transitional forms, the three important groups here are synapsids, anapsids, and diapsids. Every actual reptile you've ever seen in your life was a diapsid. As they diversify and their biology continues to develop, most of them look superficially like lizards, except for these guys. Look what's happening here. This is an excellent demonstration of macroevolution within a single clade. These specimens represent only a quarter of the species known from this group, so the phylogenetic tree is enormous and extremely complex. The family tree of all modern reptiles has a deep fork that begins right here, between the two main branches of Lepidosaurs and Archosaurs. On the Lepidosaur side, we have vaguely lizard-like forms, which is a very generalized design with a lot of potential development in different directions. For example, here we have another set of marine adaptations. Here are your plachodonts and plesiosaurs, pliosaurs, and nothosaurs. Further out on this limb, we have the order Squamata. These are the actual lizards, real lizards, including everything from skinks to snakes. Geckos, iguanas, goannas, Gila monsters, and horny toads, as my family referred to them. Everything that really is a lizard belongs right here in this group. This is a taxonomic order comprising 9,000 extant species, while every remnant of all these other clades is now extinct, with only one exception. Sphenodonts from New Zealand are the last of their kind. Dozens of their species are known from the fossil record, but now only the Tuatara survives. These are definitely not lizards, but they're classified alongside lizards because they do share a couple of diagnostic traits. For example, Lepidosaurs typically have 3 eyes. Now, you may have caught lizards as a kid, or maybe had a pet iguana and never noticed that third eye, but if you look closely and carefully at practically any lizard, you can usually find one scale directly over the brain which is a slightly different color than all the others. This eye is connected to the pineal gland. It can only distinguish light from dark, but these are cold-blooded animals, and tests have shown that this eye is critical in determining how long they need to stay in the sun in order to maintain the correct body temperature for the amount of food energy they have stored. Now we'll compare Leptosaurs to Archosaurs. The smaller of these two is a crocodilian, which gives you an idea how big the other one is. The larger one, with flippers instead of feet, is a mosasaur. There are several species of this too. They're actually lizards, true lizards, the largest lizards ever discovered. Their closest living relatives are land-dwelling monitor lizards like the Komodo dragon. Like every other amniote, the earliest archosaurs were superficially lizard-like, but not actually lizards. Following their evolution, we come to another important fork in the road. Cruotarsi includes crocodilians and other things that look and act like crocodiles, but we're not interested in the primitive archosaurs. We want to see the really advanced ones. That's where we find pterosaurs. As you can see, pterosaurs are very close to the origin of dinosaurs. This is the simplest way I could show this group fairly. The grouping is generally divided between the usually large pterodactyloids and long-tailed rhamphorhynchoids, but not all of the relationships therein are firmly resolved. There are a handful of specialists who each have slightly different arrangements being reconsidered and revised. That's not the controversial part. These few trivial differences are the result of honest estimates of expert analysis within the range of human error. There's going to be some disagreement. The controversies have much worse implications about the characters behind them, but before I can explain that, you'll need to know some of the backstory. Before Darwin was famous, England was already a leader in paleontological studies, due largely to an intrepid fossil hunter named Mary Anning, although she didn't get much recognition at the time, partly because she was too poor to associate with academic aristocracy, and partly because she was labeled a religious dissenter, but she was primarily prohibited from participation simply because of her gender. The Geological Society of London was an old boys' club with no girls allowed. Experts consulted with her, but her name was not included in any of their publications. Mary Anning died in poverty and relative obscurity in 1847, and the significance of her contribution to science wasn't formally recognized by the Royal Society until 2010, 163 years after she died. 200 years ago, when she was just 12 years old, she co-discovered the first ichthyosaur fossil ever found. She was also the first to discover a plesiosaur, and she found the second pterosaur, Dimorphosaurus. A pterodactylus had already been discovered in Germany. Neither of these pterosaurs were very big, so they weren't that different to Victorian eyes from bats or birds. Soon after, other curious fossils came from the British Geological Survey, representing as many as a half dozen species of gigantic reptiles, unlike anything alive in the modern day. The first one was identified by a single tooth, which looked like an iguana's tooth, only much, much bigger. So it was named Iguanodon. Even when more of the skeleton was found later on, it was still fragmentary and not well understood. Sir Richard Owen was a renowned anatomist of the Royal Society when he described Megalosaurus. The Latin name essentially means big-ass lizard. He recognized traits shared in common by these giant lizards, from the fused sacral vertebrae in the pelvis to the fact that the legs don't sprawl like lizards or crocodiles. They were more like mammals in that the legs supported the weight directly, like columns. In 1841, he classified these specimens together under the name dinosaur, a word meaning terrible lizard. But that wasn't the way Owen meant to describe them. He wanted them to be fearfully great lizards, perfect creations in their original form. And yes, he thought they were created. Decades before Darwin ever published his theory of natural selection, many scientists had already suspected that evolution happened. They just didn't know how to explain it. Owen, however, was a creationist, albeit not like we have today. As a paleontologist, Owen was the leading authority in the world of his time. He knew better than anyone about the progressive stages shown in the fossil record, and this caused him to reconcile things in an unusual way. Where today's creationists talk about the baraminology of created kinds, Owen believed in archetypes of divine design. A lot of people who have read his work have commented that it's hard to make out exactly what he's talking about. He's not always consistent, and he contradicts himself in confusing ways, but it seems as if he had the idea that God would occasionally release new and improved models to replace the old series once they've worn out. so that megalosaurs and iguanodons were replaced by mammalian predators and prey. That's why we had ichthyosaurs in the past and dolphins now. This was his explanation for why the fossil record for pterosaurs ends before the fossil record for birds begins. At least that's how it seemed in his day. Like many creationists, Owen had the impression that evolution meant a ladder of steadily increasing complexity and progressive advances to achieve higher forms, but he recognized that dinosaurs were bigger and better than any modern reptile, and to him that meant that they couldn't have evolved. Instead, he said that these magnificent monsters must have degenerated over time to become the sluggish, cold-blooded, barely functional reptiles we have today. Amusingly, as more fossils were found and these forms were fleshed out, it turned out that dinosaurs were even more advanced than Owen had imagined, and this presented some problems for his position. Dinosaurs turned out to be much more bird-like than he was comfortable with. Another anatomist named Thomas Huxley, famously known as Darwin's bulldog, saw Owen's Megalosaurus and immediately drew a connection with flightless ratite birds like ostriches and emus. He argued that birds were essentially reptiles, and he remarked on the obvious similarities of their hind legs. However, the rest of the scientific community was not yet able to imagine how one could evolve an ostrich out of an iguanodon, and there was a good deal of argument over which traits were inherited and which traits were convergent. These arguments, by the way, were carried out in public literature. You publish your argument and piss off the people who then publish their counter-arguments against you. It's not a lot different from the blogosphere, just really slow. But there's hardly any trolls. Now, as soon as anyone saw what a theropod foot looked like, they pointed to trackways that had previously been attributed to giant birds of enormous proportions, and they guessed that these must have been the tracks of dinosaurs. Owen had successfully silenced a lot of these claims when he reconstructed the skeleton of a moa from New Zealand. Here was a gigantic bird capable of making many of those tracks. That ratite birds and dinosaurs had exactly the same shape and structure to their legs was, according to Owen, a borrowed trait. Essentially the argument of common design indicating a common designer, except in this case it was one who could freely swap parts from other products like a manufacturer of machines. Owen was trained in Linnaean taxonomy, which presented fish, amphibians, reptiles, birds, and mammals as separate categories where it was impossible to derive one from another. But these were usually rooted in fundamental commonality, which Owen didn't always adhere to. Owen's idea of archetypes led him to classify animals by what he perceived as their unity of type. He held that reptiles and amphibians were essentially the same thing, and he placed birds and mammals side by side at a higher level due largely to their warm-bloodedness. At one point he thought dinosaurs were warm-blooded too, but he later argued against that when he didn't want anyone to see that the categories of reptiles and birds might overlap. Owen compared birds to mammals regarding their similar intelligence and behaviors like parental care. These he thought were diagnostic traits which distinguished warm-blooded animals from cold-blooded ones. He also said that the particulars in which birds differ from all mammals and agree with reptiles are comparatively unimportant ones of the skeleton. So according to him, the underlying foundational structure didn't matter, and only the superficial surface features are definitive. One may as well try to establish relationships based on whether two species are the same color. It seems absurd to us now, but at that time there were notable scientists who actually thought like that. Now here in the 21st century, I would say that evolution leads to a series of incremental changes being slowly compiled atop successive tiers of fundamental similarities, and that these tiers of similarity establish taxonomic clades. So the basic commonality matters more than the dressing of subsequent attributes. I would trace an evolutionary lineage according to that rule, and embryology would bear that out too. But people of the 18th and 19th centuries were surprisingly superficial, more concerned with the facade than the foundation. When attempting to determine the origin of birds, for example, some people actually allied them to turtles based solely on the fact that they both had beaks. Now, if your contemporaries are able to believe something as ridiculous as that, then imagine the reaction once pterosaurs were discovered. Folks readily assumed that birds must have evolved from pterosaurs despite how different their fundamental structure was. Remember, there is a traditional folklore that if you adopt the clothing and behavior of a thing, you could become that thing. And maybe that's where these ideas are coming from. Darwin, however, was unusually progressive for his time, well above the typical prejudice of judging a book by its cover. He examined life as it develops, from the inside out, rather than the other way round. He predicted that if his theory were true, there should be a bird found in the fossil record with unfused wing fingers. His prophecy was fulfilled just a couple years later when they found the first Archaeopteryx. Imagine the reaction to that. Paleontologists didn't know what to make of it. Huxley argued that giant flightless ratite birds like ostriches and emus may have evolved directly from dinosaurs, and that we see their wings as they're developing. He imagined that ostriches might fly one day. But he decided that birds who could already fly must have evolved from Archaeopteryx. Harry Seeley tried to cite Archaeopteryx as a transitional species between birds and pterosaurs. Andreas Wagner, who promoted a different type of evolution, wanted to name it Gryphosaurus, thinking it to be a pterosaur with feathers, as if that makes any sense. Now all these men eventually realized how and why they were wrong, and they changed their minds accordingly. But not Owen. Owen had a reputation for never admitting any error, except by way of evasive maneuver. Owen seized on this collective confusion to devise another wedge between birds and reptiles. He largely ignored Huxley's minority opinion that birds had evolved from dinosaurs, and instead tried to strengthen the link to pterosaurs that was suggested by Wagner and Seeley. Owen wrote a detailed report comparing Archaeopteryx to Pterodactylus, in which he conceded that every bone in the bird was antecedently present in the framework of the pterodactyl. The way he phrased it, it seemed that if birds had evolved from anything, pterosaurs had to be the closest link. Having built on that illusion already endorsed by the majority of his contemporaries, Owen then went on to describe how other details made it impossible to derive the structure of birds out of the template provided by pterosaurs. Owen hadn't yet succeeded in keeping birds and reptiles separate. There was still the issue of Archaeopteryx's long tail and grasping wing fingers. So Owen examined Archaeopteryx and found a subtle feature in the ankle that was still uniquely avian. Thus he described it as an unusual bird, but still just a bird nonetheless. At the same time, he applied a double standard when he said that the unfused wing fingers, which Darwin had predicted, were relatively unimportant. So all that matters are whatever supports Owen's argument, and when it doesn't, it can be dismissed without consideration. Owen had a reputation for spinning information to make it look like it supported him, and he wasn't above making things up to suit his position either. Huxley had called him out on that before. These men famously viewed each other with contempt. When they posted their studies, they included criticisms against each other like a flame war. Can you imagine professional scientists in the modern day berating each other in the public media? So Owen made a prediction of his own, hoping to counter Darwin's. The first Archaeopteryx fossil ever found was missing its head, so Owen predicted that later finds would show that it had a normal, toothless beak like all other birds known to that time. Of course, later finds proved him wrong. First of all, fossil birds turned out to have teeth in their beaks, just like many pterosaurs did. But worse than that, it turned out that Archaeopteryx didn't have a beak at all, just a reptilian maw full of teeth. However, before anyone knew any of that, another dinosaur, a non-avian dinosaur, had already ruined Owen's prediction and his position. Now, I told you that scientists of the 18th and 19th centuries were superficial, judging affectations over foundation. Here's a demonstration of that. Not all of the Archaeopteryx fossils left feather impressions. 2 of them didn't, and for that reason they were both assumed to be something else. Having no detectable feathers to confuse anyone, Compsognathus was classified as an unambiguous dinosaur using all the same criteria which Owen himself had already listed for that taxon. Archaeopteryx has longer arms and a wishbone, but otherwise these skeletons were virtually identical. Carl Gegenbauer studied the tiny chicken-sized dinosaur and discovered that it even had the same ankle as Archaeopteryx, so that trait wasn't uniquely avian anymore. In fact, the only trait that skeleton showed that was uniquely avian was where the collarbone had fused into a furcula, or wishbone. Wishbones have since been found on Deinonychus, and then on Allosaurus and Tyrannosaurus, and a host of others. In fact, no part of Archaeopteryx skeleton is uniquely avian, as is obvious once you compare it to this chicken. Coincidentally, many have argued, including myself, that it should not be correctly defined as a bird, but that it is definitely a dinosaur. Now even Seeley was convinced, having become something of an expert of pterosaurs as well as dinosaurs. Soon he found himself bashing Owen too, because Owen cast pterosaurs as cold-blooded, sluggish gliders. He admitted that they had hollow bones just like birds and dinosaurs, but again he tried to suppress the importance of that, and the implication that these animals were warm-blooded, highly energetic, and very strong flyers. Seeley knew better than Owen, and he published his conclusions in 1901. But because Owen was perceived as an authority, his word held sway, so that 100 years later, scientists are still arguing over whether these were all cold-blooded reptiles. That's how all the books depicted them when I was a kid. Seeley divided the dinosaur clade into two halves, the lizard-hipped and the bird-hipped. Of course, he initially thought that birds must have evolved from bird-hipped dinosaurs, but as we move down the lineage of the lizard-hipped variety, the fossil sequence shows the pubis bone moving into the avian position. We also find fossil impressions revealing four-chambered hearts and every attribute once believed to belong to birds alone, including gizzards and gastroliths. We found quite a few dinosaurs that are very close to birds, and some are so close we can't tell whether they're birds or not. We've also found a few lines that are definitely not birds, yet they had feathers. We've learned more about the paleo world in the last couple decades than in the past couple centuries prior. For example, here are the Velociraptor and Oviraptor from Disney's movie Dinosaur, which was released 14 years ago at the turn of the century. At that time, these animals were both depicted naked. However, since then there have been some interesting discoveries. First of all, velociraptors have the same quill burrs in their forearms as vultures have, implying that they had wings even though they couldn't fly. Why would that be? And what would they use them for? The answer comes from its closest cousin, the oviraptor. Its name implies that it stole eggs because they were always found with eggs around them. But then we found this fossil. Duh! It's sitting on a nest like a chicken. What more proof do you need that it's warm-blooded? Look how its arms are draped over the eggs outside. You can't warm eggs that way unless you have insulating wings. Traits like this provide strong selective pressures in the evolution of species having nothing at all to do with flight or escaping predators, so velociraptors and oviraptors might well have looked more like this. Yes, we now know that even tyrannosaurs were fluffy. In the same year that Disney's Dinosaur came out, a fossil was discovered which confirmed how dinosaurs adapted their feathers for flight. It was a four-winged glider called Microraptor. An ornithologist named C. William Beebe detected a trait in Archaeopteryx which most others had missed, the fact that it had a few flight feathers on its hind legs. They weren't enough to be useful, so he proposed a hypothetical earlier form which he called Tetrapteryx. He didn't know that we would call it Microraptor because this illustration of his prediction was published a century ago in 1915. This was someone who was definitely on the right track. Now let's talk about someone who was determined to be on the wrong track. After everything I just told you, how could it be that we still see stories like this cropping up again and again? One explanation is that every time you see this claim, either in the peer-reviewed literature or in the popular press, it's from the same author every time. I always say that it is dishonest to assert as fact that which is not evidently true, but it's worse when you decide in advance that you will reject any and all evidence that may ever be brought against your assertions, but there is a handful of scientists who have conspired to do exactly that. In the 1990s, John A. Rubin and Alan Faduka gathered together a few of their associates and formed a collective called BAND, B-A-N-D, Birds Are Not Dinosaurs. Their mission statement was to deny every indication that birds had emerged within and were descended from dinosaurs. They proposed instead that birds had evolved from a common ancestor with dinosaurs. Their last good argument was that birds have a network of lung sacs attached to hollow pneumatic bones which allows them to breathe far more efficiently than other animals. They can even breathe through their bones. The argument was that the avian respiratory system could not have evolved from the hepatic piston system of crocodiles and presumably dinosaurs. Notice that this article was posted in 2009. The first time I read that argument was in 1999, and that argument was refuted in 2005 when it was discovered that Archaeopteryx and a number of non-avian theropods, including Allosaurus, had skeletal indications of fully avian respiration. This fact has not stopped the bandits, as other paleontologists have come to know them. They are still repeating the same argument they now know is wrong. We now know for certain that birds are living dinosaurs. This is the consensus among scientists, and every article you ever find that argues to the contrary will have Rubens or Feduca's name attached to it. They also claimed that fully developed flight feathers could evolve independently outside the lineage of dinosaurs, and that they had evolved long before dinosaurs. This connects to the last controversy of this lecture, but before I can get into that, we need a few more details. Feathers are complex structures made from multiple sequential stages of development. They start out as a tubular bud of skin. Inside it, bud ridges begin to form, and a pattern begins where the emergence of new barb ridges on one side moves the others to combine into a central shaft. Additional ridges fuse to the shaft and eventually spread into the first branching fronds of a true feather. So we have a hollow spiky tube, then a downy feather tuft as the tube divides into disconnected barbs. When the next generation has barbs growing around the tube, they form a rachis. Then the barbs grow barbules and a series of matching connections to zipper the fronds together, and there is a complete double-veined feather. Each of these stages is well documented in embryology, and each stage is also mirrored in the fossil record of the evolution of theropod dinosaurs. Now, different types of animals have independently evolved different types of eyes and other structures of different designs which are each unique to that lineage. But such a precise alignment of this sequence of these particular developments could not reasonably have evolved twice. Fully developed feathers are a one-time occurrence. They first appear in theropod dinosaurs, and they've been inherited by birds. There is no possible alternative to this scenario. That is not to say that pre-feather filaments didn't exist otherwise, or that plumage should always follow the exact pattern of the evolutionary development that we see in birds. The most primitive feathers we can still see are found on paleonate birds like emus. This is probably the most famous image there is of an emu. Look up emus on Google Images, and this picture usually comes up first. This photo was taken in a park a block or so from my house. We took this picture in the same park on the same day. Our bird was 4 months old at that time, and you can see that what passes for feathers on his head seem indistinguishable from very fine hair. The most primitive form proto-feathers can take would be hair-like downy fibers, and such delicate features would rarely leave recognizable fossil impressions, yet this sort of thing has been found on early theropods and also in pterosaurs. This is not to say that pterosaurs had proto-feathers. The structure is different, but some sort of pycnofibrous precursor apparently preceded proto-feathers, and actual feathers did not exist before dinosaurs. True feathers belong to theropods and their descendants exclusively. Reverend Robert Bacher, Ph.D., once suggested that pterosaurs should be considered dinosaurs, but that would only be if we changed the name of Ornithodira to Dinosauria or Dinosauromorpha, and there's no justifiable reason to do that. Ornithodira are the highly advanced archosaurs, not the primitive ones like crocodiles. This clade could be identified by the emergence of hollow bones and perhaps the emergence of pycnofibers as well, but that doesn't mean that everything descending from these groups would have both of these traits. Hollow bones are rare in ornithischians, and large dinosaurs wouldn't always have insulation. Look at elephants or rhinos. But it would mean that the precursors of feathers weren't limited to theropods alone, and what we know about evolution means that if we go back to the beginning of feather development and start all over again with ornithischians, we could get something very different. For example, what if the tubular bud spikes just got bigger and the barb ridges never splayed out but kept rigid? That would explain the weird spines that they found on the tail of Psittacosaurus. And since this animal is considered to be ancestral to ceratopsians, it makes sense that evidence of something similar was recently found in the skin impressions of Triceratops. Have I sufficiently ruined your impression of Jurassic Park yet? Let's just ruin all the movies about pterosaurs. They could soar like airplanes, but they couldn't hover like hummingbirds. They couldn't carry things with their feet either. They couldn't perch on tree branches like birds. They didn't look like giant bird monsters, and they didn't look like lizard bats. They didn't have four-fingered wings like bats. Their wings were based on an elongated pinky finger. The only thing bat-like about them was the way they walked, on all fours. So what are the possibilities for fluffy pterosaurs? We know they were a very diverse and almost certainly a colorful group, and they looked like a wide range of things, from fluttering bats to darting falcons, and some had powerful shell-crushing jaws, and some had ridiculous crests, and some were quite huge. For decades we were told that Pteranodon was the biggest animal that ever flew. Then they discovered Ornithocheirus, then Quetzalcoatlus, then Hatzegopteryx, an apex predator. If the painting seems like an exaggeration, let's look at a scale model. These were capable killers of even human-sized prey, with a skull larger than that of even the biggest carnosaurs. In their evolution, we see that the earliest pterosaurs were small and yet still unnecessarily heavy and clumsy, both in the air and on the ground. But 160 million years of refinement has honed their abilities to the limits of incidental engineering. Despite their enormity, they were unbelievably lightweight. Even the biggest ones were estimated at less than 500 pounds. They had hollow pneumatic bones of large diameter but only millimeters thick, making a strut-supported tubular frame that is surprisingly strong and highly resistant to the stresses of aeronautics. They also had extraordinarily powerful wing muscles, and this made them capable of vaulting airborne in a single bolt. Once in the air, muscle strands and tendons in the membrane of the wing itself worked with a network of pycnofibers to give them all the data they needed for subtle adjustments to the shape of the wing. The portions of the brain which are dedicated to flight, balance, and visual gaze stabilization in birds are all larger and more adapted in pterosaurs. In fact, scientists are now convinced that these animals had such a mastery of flight that the larger ones could even cross oceans, going 80 miles an hour at 15,000 feet for thousands of miles on a single launch. But what about the origin of pterosaurs? It's tempting to consider that they might have descended from the weird Triassic glider Charovipteryx, but it's only known from one partial fossil, so scientists don't have enough data to go on. Now it is important to note, for all the reasons I've just explained, that every evolutionary scientist yet discussed accepts that dinosaurs, birds, and pterosaurs all belong in the clade Ornithodeira, and that since the days of Seeley and Huxley, the closest fossil ancestor of all archosaurs was believed by all the experts to be Euparkeria due to its specific characters. However, if you Google pterosaurs today, you'll likely see a very different explanation provided by a talented and prolific paleoartist named David Peters. Peters is an independent researcher, unaffiliated with any academic institution and without any qualifications in geology or biology. Yet, he is standing up to experts in ways that just don't make sense. It's a life's work of extensive errors that I can't adequately address in this talk, so I will summarize. Peters says that everyone who has ever studied pterosaurs is wrong, and that pterosaurs are not actually archosaurs, even though they have all the characters of that clade. He says pterosaurs are lizards, actual lizards from the order Squamata, even though they don't match any of the conditions for that classification. He says pterosaurs are descended from an earlier lizard that he says had fully avian, double-veined flight feathers, even though pterosaurs don't have feathers themselves. I mean, I've argued against traditional taxonomy. I said that apes are descended from monkeys and that humans are still monkeys right now. I said that scorpions aren't arachnids like spiders, and that they and arachnids arose separately from within the clade of Eurypterida, giant sea scorpions. But when I have to argue that to scientists, they come away accepting that I might be right. Peters, however, bases his analysis on subtle blips and shadows that only he can see in JPEG images blown up on his computer. Then he draws conclusions based only on that, which are often not demonstrable to anyone else and can't be shown in the actual fossils and which are inconsistent with all available data. For example, Peters and John Rubin of Band both share one common delusion, the idea that an ancient lizard called Longosquama had feathers. Here's how it's usually depicted, as if it were capable of flying like a butterfly. It's a common misconception, with many depictions showing how its wings are splayed out. Peters himself says it's almost certainly a glider. However, Longosquama didn't have wings. Here's how it looked according to a pterosaur expert. When David Peters looked at this same fossil, this is what he saw. Not only did he find the back half of the skeleton, which no other scientist has been able to detect, but he described it as bipedal, with flapping arms, extremely long fingers in the hand, with a wing membrane attached to the fifth digit, and a hind leg wing membrane as well, and a tail vein made of hair, none of which is evidently true. More importantly, these are not feathers. At a glance, they may look like feathers, but they look more like sculptures of feathers than fossils of feathers. We know what fossil feathers look like, and they don't look like this. There are a couple features which betray the reality. The repeating dimples indicate that these are not feather veins, but solid, albeit thin, membranes. The three-dimensional outline around each one shows much the same thing. These are elongate scales, not feathers, and scientists have been saying that since this animal was discovered. The real problem is that nobody's listening to the scientists. They're looking at the sensationalism of personal homepages inspired by the popular press, and Peters has exploited that. He's bypassed the peer review process, refusing to admit where it must be he who is wrong and not every one of the world's experts who has actually seen these fossils with their own eyes. He has exhaustively rewritten the phylogenies of all these fossils in his two websites, Pterosaur Heresies and ReptileEvolution.com. And he has flooded the internet with his drawings. His work looks so good, and he's so prolific, and he's been at it so tirelessly for so many years that he has effectively drowned out any real science resource on this subject. Any layman interested in learning about the evolution of turtles or pterosaurs will likely believe they're looking at the work of legitimate science, but it's all wrong, and it's remarkably wrong. I've spoken to a number of paleontologists specializing in pterosaurs, and they're glad that I'm giving this presentation to call attention to how the public has been repeatedly misdirected by those with a bias, or an agenda, or an inadequate understanding, or an overactive imagination. I'm following their directive that people who understand how ideas are investigated and tested should take an active role in communicating science, especially when misinformation runs rampant. It's rather like when you come to trust the Science Channel or the History Channel, and you find that either one has suddenly started talking seriously about extraterrestrial reptiles secretly infiltrating our government. We need a healthy dose of skepticism, and we need to call out bullshit when we see it.